All right, so that was an example with, or ending with an example, the last video anyway, with the Coulomb's law. The next idea is this idea that there are actual fields, an electric field and a magnetic field, and the fields will interact with charges themselves. So the charges actually create the fields, but the charges can be really, really far away. I mean, literally, millions and millions of kilometers away, or it doesn't even matter. It could be halfway across the universe. But if the field is strong enough, it'll interact with other charges, and these fields travel at the speed of light. They do have a velocity. Anyhow, the main idea here is that if the electric field encounters a negative charge, it will react with that negative charge. If it encounters a positive charge, it'll react with that. And so generally what they do is they take this positive, they consider it a positive test charge that's coming from, let's say, a charge that, or let's say there's a electric field that is created by a negative charge. So the negative charge can be really far away, and what does this positive test charge do? Well, since this is a negative charge and it's a positive test charge, the positive test charge will be attracted to whatever direction that negative charge is. And it works the opposite way, of course, with an electric field that is created by a positive test charge. So, I'm sorry, by a positive charge, and then you have a test charge some distance away. It doesn't really matter how far away, but when this positive test charge interacts with the field, it will be repelled, because that field is basically, you might think of it as being pushed away from this original charge that made it up. All right, and we go as far as to even create or show these electric fields. This is, of course, just in 2 dimensions. Magnetic fields look the same. They're actually 3-dimensional objects, so mathematically they're very, very difficult to deal with. But for example, here's 2 positive charges, and notice the fields are from the 2 are not crossing at all, and they don't, for example. And then let's see, let's take a look. So this is a positive and a negative, and notice the positive arrows leave the positive charge going away from it, and then they terminate on the negative charge. So these are the electric field lines in 2 dimensions. All right, and of course, just to the negative charge, if there were 2 negative charges, it would look the same, but the arrows would be pointed the other way. Okay, so we're not really going to do anything with that. Here is an idea that is very much related to the chapter on energy, the chapter 4, which was about energy. So this is what we call electric potential, and it is related to energy, but this thing called electric potential is better known as volts. Okay, so they're used interchangeably. Electric potential and voltage are the same thing, but there is a relationship between electric potential and work, and so we'll do a quick example with this formula. So the work is equal to the charge times the voltage. All right, so let me set up an example. All right, so here's the same formula that I was just showing you in the PowerPoint, but let's go over what the units are here very quickly. Work, of course, is always in joules, so joules will work just like energy. The charge is going to be in coulombs, and the voltage, V, is in volts, or better known as the potential difference. Okay, so a joule is a coulomb times a volt. And now what is a volt? Okay, so voltage is this electric potential difference between 2 points in space. And they can be any 2 points, okay? So you have a point A right here, and here's another point B right here, and there happens to be a charge over here, Q, near our point A. Now, to move Q from A to B in terms of electrical work, as long as there's no voltage between points A and B, then it requires no work at all, right? No electrical work, that is. But if there's a voltage between point A and point B, all right, so let me indicate that. Like if you had a voltmeter, here's our voltmeter, and you put one lead on point A and one lead on point B. This is the same type of voltmeter that you would use, for example, to measure the voltage in a battery. If there's some voltage between those two, and we'll call that voltage V, okay, nothing very surprising here. If there is a voltage between point A and point B, then it will, to move the charge Q from A to B, to move this, will require work, electrical work. All right, and that's of course, this equation here. All right, so let's do a quick example. This is not terribly difficult. All right, so in fact, I'll just use this here. Let's say the voltage between these 2 points was, I don't know, how about 150 volts? Okay, and so it looks like that. And the charge Q is, we'll make it a little interesting. Let's say it's 3.9. Now see, a coulomb is a huge amount of charge, so generally you don't really see coulombs of charge. I mean, sometimes you do, but that's actually pretty rare. In normal electronics, for example, that you would find in a computer or in a television or something, or your cell phone, you're talking about very small amounts of charge. So let's say it's 3.9 microcoulombs. That's a C. All right, and so we want to know how much work it takes to move this charge, 3.9 microcoulombs, from point A to point B. And of course we have this formula. The only problem is Q, as it says over here, must be in coulombs. And it's not right now, it's in microcoulombs. So as usual, we have to change the units. So 3.9 microcoulombs. So Q equals 3.9 microcoulombs. And that's equal to 3.9. And micro, if you remember, is times 10, the metric prefix, micro is times 10 to the minus 6th coulombs. And so we just multiply to figure out the work. It's going to be 3.9 times 10 to the minus 6th coulombs times our voltage, which in this case was 150 volts. Notice if you increase the voltage, the work would increase. If you increase the charge, the work would also increase. So let's figure out what this value is. So when I do this with my calculator, I'm getting a value of 5.85 times 10 to the minus 4th. And since of course we're talking about work, it's in units of joules. Alright, so 5.85 times 10 to the minus 4th joules. Alright, so we did that. Electrostatics, I think I mentioned this before, is when the charge more or less stays put. There is an excess of charge, or too little too few electrons, which would still constitute a total charge, but it would be a positive charge. If there's too many electrons, it would be electrically negative. Now, when when charge moves, we have a name for that. It's called electric current. And electric current occurs because there's a potential difference, or there's a voltage. So the voltage you can kind of think of as the cause of electric current. Okay, and of course we have lots of electric, circuits these days. This is not, well, this is a good example, I suppose. So current, let's say, flows, and don't ever get confused about this. This was established a long time ago just as a standard, is that current flow is always from the positive, and of course here's the device, the electrical device. In this case it's a light bulb, and then the electrical current will terminate on the negative side. Nowadays, of course, we realize that it's electrons that are flowing. When Benjamin Franklin originally set up the idea of positive and negative charge, then people really didn't know what was flowing, and so we stick with this unfortunate convention where it's positive charge that's flowing, when in fact we know it's actually negative. But don't let that get you confused. Charge has to flow. There has to be a complete path. That's really important. So if there was an open in the wire right here, if the wire was cut in half right here, or even right here, anywhere along this electrical path, then current would stop flowing and the light bulb would go out. Even if you cut the wire right here, right? I mean, it doesn't. This does not occur. A lot of people think it does, but they would think that the current would flow through the light bulb, through the electrical device, and then basically, because it was cut right about here, then the electricity just stops. But that's not the case. You have to have a complete path for these electrical devices to work. So there has to be a full, complete path. All right, so let's going to skip that. We'll skip this too. So this is the definition of current. Current is the charge divided by the amount of time. So it's actually a delta Q over delta T, but usually the initial charge is zero and the initial time is zero. At any rate, the current is measured in units called amperes or amps. So what does this formula tell us is that the charge Q, which is in coulombs, divided by the time, which is in seconds, is equal to a certain number of amps. And there's actually two types of current, as you probably know. There's direct current. Direct current only flows in one direction, so that's the thing that you have to realize. That's the kind of current that comes from batteries, or it's actually the kind of current that's used in most electric devices. What happens is there's an electric device that usually changes AC, which is far more common and easier to produce, as far as cost. Than direct current. Like to run something on batteries turns out to be the most expensive way to run an electric device. So usually what we do is we'll convert some of the AC into DC. So DC it's charge that moves only in one direction. So let's go back to one of these. Only moving in one direction. So that would be the battery is a great example of direct current. If you had a generator here, an electrical generator, what happens is the current goes one way and then it'll go back the other way. And so that's what we mean by AC, or alternating current. So the motion is back and forth. So the direction of the current is one way and then the other way. And another way of saying that same thing, it turns out, if you look at it mathematically, is that there's no net current flow. All right, and let's see. Well, this is called Ohm's law. We'll get to that shortly. I want to do a quick example of